All right. If we look at the review sheet, we can see that we've got, the first thing is refraction. And one thing you need to realize is that this is the more dense medium. And that is not going to write, so let's get an actual pencil that writes. This guy, does this guy write? Maybe. So this is more dense, right? But it also means that it's slower, okay? And that's the important thing. And if it's slower, we know from working with refraction that we mean that the angle will be smaller, right? The angle is going to be smaller. Right? For air, it's less dense. Right? So it's faster. And that means a bigger angle relative to the normal. And so we have our normal line here, and so this angle should be big relative to the angle out here. So all we have to do to draw our refraction line is we simply set it parallel to this arrow for a second, and then we just turn it a little bit so that it's a smaller angle. So we get a smaller angle, something like this. And if we give ourselves a pencil tip, we can draw our smaller angle. And so the light should pass through this block, right, closer to the normal line, because this is our small angle. So big angle here, small angle here in the slow medium. Now, when we get to the other side, we have to draw a second normal line, and that normal line is supposed to be perpendicular to the surface. So we move our ruler so it's kind of straight up and down, and draw a normal line, right? So here's our new normal line. And then now it's coming through to this side, right? It's going to be somewhere in this region, but it's going to be a bigger angle, right? Because again, in this medium we have a smaller angle, so this will also be a small angle. And that means that on this side we should get a bigger angle, so we'll simply put our ruler over here parallel to the ray, and then we'll simply twist it a little bit to make the angle bigger than it was. And since it's technically the same medium, it should really be the same angle it was before. Right? And so it should really come out about like this. Okay? So if we look at this, here's our bigger angle. Okay? And so it should come out of the medium, right, sort of the way it came in, right, since these two sides are parallel. Right? So it goes from big to smaller, and then from smaller to big. Now when we look at this side, we have, we've reversed the media, right? So now this is our slow medium, right? Because it is more dense. And that means it should have the smaller angle. Okay? So if you look at this, here's our slower medium and more dense, smaller angle. So this should be small this time. Small. So what we'll do is we'll line up our ruler, but instead of making it small, this time we're going to make it bigger. And so we'll twist it a little bit away from the normal line, and we'll make our bigger angle, and we draw our line. And the ray goes through the medium, right? So this is now our bigger angle, right? And then we draw another normal line. And so we simply take our ruler and try to make it as perpendicular as possible, and we draw another normal line. And now this is going to be our big angle, because this is our less dense medium. Right? Which means it's faster, and it means big angle. Okay? So we line up our ruler with the line, and we simply rotate it to make our smaller angle again. And again, since it's, if we line it up like this and twist, right, we can twist until it's parallel with that original line again. And because since we've got a rectangle, it should come out of the rectangle at the same angle that it went in. Okay. So here's our small angle, right, like this. So we measure everything from the normal line. You know, it's tempting to want to measure it relative to the surface, but we always measure it relative to this perpendicular line. So if this is our big angle, this is our small angle. So small, big, big, small. Okay. So refraction is pretty easy as long as you identify the two media, and then you can tell which angle should be bigger, which angle should be smaller. Now the next question says to sketch the ray diagram for the following object and lens and show where the image would form. There are only 3 rays that we can draw. One should be parallel to the axis of symmetry, and so we simply draw a parallel ray. Now we take it to the middle of the lens because the lens is usually assumed to be pretty infinitely thin, so we just draw it to the middle of the lens. So this is our parallel ray. And if it's parallel, right, when it's going towards the lens, it's going to refract through the focal point. And so we would draw it through here, and we would get our refracted ray through the focal point. Right. And so if it goes into a this is a convex lens, and a convex lens takes the parallel ray and puts it through the focal point that's on the opposite side from the object. Right? Now, I can draw 2 other rays. One ray would simply be to go through the center, and if you go through the center of a lens, and it doesn't matter what shape of lens, the ray doesn't change directions. And what we find is that I didn't leave you enough space. Say through center. And you're unchanged. Okay. And what you see is that they would converge, but they would converge over here off the paper, right, which is sort of cheaty. But if I had another sheet of paper, I could extend this a little bit. And it would look like the it looks like the 2 rays should converge over here. Now, you're probably not going to care to do this, but it would look like something like this, right? So it converges over here. So converge off the paper. Now we can actually draw a 3rd ray, and the 3rd ray would be through the focus. Now if we can't actually draw it through the focus, we would draw it as if it went through the focus, but this time we can because the object is farther than the focus. And you can see that I didn't leave enough space because this ray goes below the lens, and we would sort of have to pretend that it hits the lens. But through the focus, it refracts parallel. And so parallel would be, I don't know, something like that. And you can see that our 3 rays come really close to converging with each other. So our convergence would be somewhere over here, right? Right, parallel to the axis of symmetry, right? And so we get our convergence over here, which means that our image would be over here, and the object would be flipped upside down. And we know it would be flipped upside down because this is the top of his head, and so the top of his head would be over here, That's why we use a person or an arrow or something, because we can tell which end is which, and it would look something like this, right? We'd have our little stick figure upside down. Okay. And so, yeah. Now, is this image real or virtual? Well, there are a few things that we know. The actual light rays, right? The actual light rays converge. Right, we didn't have to play any game where we were tracing them backwards. So the actual light rays converge. The image is upside down. Right? And the image is on the opposite side of the lens from the object. These are three characteristics of a real image. And so we know that this would be count as a real image. Right? So that'd be our real image, and that would mean that we could cast it on a screen, right? So we should be able to cast this on a screen. Right, like a movie projector, or like these things we've been doing in class. So yeah, how can I tell? Because the actual light rays converge, the image is flipped, and the image is on the opposite side of the lens from the object. So object, lens, image, right? And so we can cast that on a screen. Okay. So let's play with the stuff on the back. Now, in this case, we've got this spectrum, and we need to compare it to our other spectrum. And we can do that you just need a copy of it. So we can take a spectrum like this and compare it. Now, this spectrum here is not in color, but we know that these guys over here at 650, right? At 650, you're somewhere in this region. So this would be red, right? But you can see it's fairly faint, right? At around 6, this looks like what? 610, 20, 30, 40, 50, 610, right? So 610 is somewhere over here. We're still red, but this is a pretty bright red line. This is just below 500. So just below 500, this is green looking. This is pretty green. Right, and it's pretty bright. And then at 460, now at 460 we're talking about something that's fairly blue. It's a bright blue line. So it helps to know what colors we're actually talking about. It would be nicer to see it in color. And it looks like there may be a line down here, but the Xerox didn't include. So we really only have 4 clear lines. 3, a bright blue, a bright green, a bright red, and then sort of a faint red line. So if we look at these, we're looking for something that has that pattern. Now beryllium actually seems to have all of these things. It could be beryllium, but it looks like beryllium has a really bright red line down below. I guess that's right. It has a bright red line somewhere here below 630, and then it has some fainter lines above, and it has a green line here and some blue lines here. So this could be something like beryllium. Okay, and all we'd have to do is check to see if there's a better match. Now, if we look at this one, like carbon, it's got a red line that's kind of faint, but then it's got this really bright line right here. But this bright line is actually less than 600, right? It's down here around 595 or just about 600. So it's actually over here and not where this is. So that doesn't look like a great match. Plus it has this really nice bright green line somewhere between 525 and 560, so somewhere in this region. And we don't have any bright green line here. So carbon looks like a bad match. Now we could look at hydrogen. Hydrogen has a nice red line around 660, somewhere here. Maybe that's it. But it doesn't have any bright red line at 610, right? There's no 610 line, right? So kind of hydrogen looks like a bad match. Plus it doesn't have our bright green line around 500. So it's missing a couple features of it. Helium has a red line around 665, so maybe that's it. But it doesn't have anything around 610 at all. And then all of a sudden it's got this yellow line here for helium, right around 590. So we're missing this line here for in this spectrum. So this helium would have a line somewhere here, and this line doesn't show up in helium spectrum. So that seems like a bad match. We could look at lithium. And if we look at lithium, let's see, lithium has a line at 665, which could easily be this guy, actually a little above 665. So this is at 670, that's a little above 665. So 670, right? So that looks like 670. It has a line somewhere here between 595 and 630. So if that's 630, then this is somewhere around 610. So this could easily be the 610 line. Then it has this bright green line down here around 500. So that looks pretty good. And then does it have a blue line at 550, 455, or 460? Yeah, it does. So lithium has all of these lines. So of the ones we've seen so far, lithium looks like the best fit, right? We're just comparing it line to line to see if they match up, and lithium works pretty well, right? We can compare it back to the beryllium, but beryllium seems to have a lot of fairly bright lines that don't show up on this spectrum. So maybe beryllium isn't a great fit there. And then oxygen has a lot of green lines, a lot of stuff between 525 and 560 that doesn't show up here. Sodium doesn't have any red lines, so it doesn't have this guy, and it doesn't have this guy, and it does have two lines in here, so that's not a great fit. And then mercury seems like it has a lot of stuff in the yellow, right? And we just don't have anything in the yellow here. So of the ones we've seen, I think that lithium is our best fit. So I'm going to say that this would be lithium. Okay. So you want to look and see what each of the lines are, and it helps to actually describe them in terms of colors and give them either a descriptor like bright or faint, so that when you're looking at the actual colored spectrum, you can match it up more accurately. But this looks pretty good. Lithium has all four of these lines and not too many lines that don't show up on this spectrum. Now, what would the absorption spectrum look like for this element? Well, an absorption spectrum is where the bands are subtracted from white light. And so that means that we would have the rainbow with dark bands. Right? So that's what an absorption spectrum. Absorption is like a sponge. Absorption means taking the bands of light out of the spectrum. So the bands would be subtracted from white light, which means it would be like a rainbow with dark bands in it. And so we would simply get Roy G. Biv here, but we'd have black bands at every place we'd have a colored band. Okay? So when we're looking at spectrum, all I would do if I were doing this, I would simply start coloring, purple to blue to green to yellow to red, and I would simply leave out something at 410, at 495, at 610, and at 670. Okay, so it would be missing light, right, or a black band. At 460, 495, 610, and 670. Okay, and so that's what I would draw if I were drawing it. Let's take this guy away and let's do the remainder. Now we have a ray diagram from an object in front of a mirror. Now this object, I would like to point out, the object is between the focus and the mirror. And so if it is, we assume we're going to get a virtual image, because this is like using a makeup mirror. Now, how do we draw the rays? Well, we draw the same three rays. We can draw our parallel ray. Okay. Except that actually I'm only going to draw two rays for this guy, because the third ray is hard to draw. But we would draw three rays. Here's our parallel ray. And we know that if it's parallel, it reflects through the focal point. Right? So it's got to reflect through the focus. Now the second ray we would draw would be through the focus, except that we can't draw it through the focus and have it hit the mirror. So what we'll do instead is we'll draw it as if it came from the focus. Now our mirror doesn't go up far enough, so I'm going to extend the mirror. I'm going to extend my mirror so that it goes farther, right? Yeah, I don't know. Should have drawn a bigger mirror. And so I'll draw a line up here right, as if it came through the focus, but it's going to start at the same point of the guy's head. So it'll be as if it came from here, but it'll go up here and hit our mirror, and at that point it should reflect parallel, and so we would draw our parallel ray, something like that. That looks kind of parallel. Let's try that. Okay. So this is as if, right, it came from the focus. As if it came from the focus. And it reflects parallel. Now the reflections in this case are diverging. You see how these guys are spreading apart? These guys are diverging. So we're not going to get a real image. Anytime we get divergence like that, we don't get a real image. Instead, what we're going to have to do is trace the line, the reflections backwards. So we're going to trace the reflections backwards. Okay, so here's one reflection, so I will trace it backwards, and I'll use a dotted line so you can tell that this isn't real light, it's just me tracing the reflected lines backwards. So there's my dotted line, right? So my backwards trace, and I'll do the same thing with this guy, and I'll simply trace it backwards. Try to use dotted lines when it's not an actual light ray, so it doesn't look like these guys, right? Now, again, we have an apparent convergence. It's not real, right? But it looks like, to us, standing on this side of the mirror, it looks like they come from here. And that would mean that the top of his head in the image would be up here, right? And he would look like some behemoth of a reflection, right? Something like this. Right? And so we would get a virtual image. The image is a virtual image. It's behind the mirror, right? The image is upright. And no actual light rays converge. So because of that, we know it's virtual. And if it's a virtual image, it can't be cast on a screen. Another way of looking at it is if no light rays actually converge, there's no image to really be cast. Okay. So that looks great. So there's our review sheet. Hopefully this is of some help. When you're done with this, what you're going to do is take the real quiz. It's got a couple more questions, but it follows the same pattern in these same 4 question types. And what I want you to do is work on it. You may use your notes. And for color, there will be a copy of the quiz in the module, and there will be a copy of the spectrum sheet in the module, so you can see the colors clearly, and you can use that to help you on your quiz. Okay. Thanks very much.